so it's getting a little noisy around here. I don't know if you could hear my son singing from the downstairs room in the last video, but I had to stop it a little early. So this is the continuation of 12.1. So hopefully you have your 12.1 packet out and your calculator still. And here is the second part of 12.1. This one will be pretty quick. There's just a few more topics to talk about. And so this is the uses of linear regression. So we just use lines of best fit using our calculator to help come up with the equation. And so here we're going to do some predictions based off of that. Okay, so a few things we need to know. The sample, so in the requirements, our sample of paired data is a random sample, of course, and it also needs to be quantitative data. So let's just think about how boring it would be if we had qualitative data. So if I took a poll of everyone in the class and I said, do you like this new remote instruction? That is a qualitative question because you would either say yes or you would say no. And if we recorded it, it would look something like from our histograms from 2, and we would have our yeses and we would have our no's, and it would always be 2 columns. It would always just be a straight up column in the yeses, straight up column in the no's. That's not going to help us. We need to have more choices. And so we need quantitative data. We need to have those number responses so that way we can get scattered answers. Okay, so step number 2 is just looking at the scatter plot. The points show approximately a straight line. So going back to that example from before with the pattern, this is not a good picture right here. This one is not a good picture to use to make predictions because there's no patterns to it, and I can't make a prediction if I don't have a pattern. Okay, and the third one is outliers be removed if they're known to be errors. And so, I mean, there can be outliers in an example. A certain baseball player or a certain basketball player may get paid way more than the average player on the team. Okay, that's fine. That's true. But we can't have outliers that are just plain wrong. And typically that's going to be where we notice our errors is in the outliers. So if you see something that's wrong, that would get removed. Okay, but that doesn't usually happen, at least not in the examples we are. Okay, so for linear correlations, we can identify an equation that best fits the data, and then we can use that equation to predict the value of one variable given the other. So here we have an example where we have the table collected on the relationship between the average minutes spent exercising compared to someone's math test score. And the line of best fit for the data is given this y hat, because this is a prediction. So y hat, I mentioned this before, but I don't think I wrote it down. That would be our prediction. Therefore, the line of best fit as our prediction line. And we're going to assume the line of best fit is significant. There's a strong linear relationship between them. So we don't have anything where there's no pattern. There's a linear pattern. It doesn't say if it's positive or negative, but there is a pattern that follows the line given. So for the first example, this is according to that line of best fit. And I'm just going to write it here because I'm going to have to scroll and we're going to lose it. So according to this line of best fit, what would be the predicted score for someone who spent 32 minutes exercising? So going up to the chart, I can see that the minutes is the first column, so it's the X. So the minute is our independent variable, and the test score is our dependent variable, our Y. So if I have 32 minutes, that's my X, and I'm going to plug that in to my equation and say y hat, my prediction, is going to be 0.44 times 32 plus 65.2. And that will result in 79.28 minutes. 79.3, oh no, not. Y is our test score. So that would be points. That would be the test score, would be about 79 points on the test. That would be our prediction. If you spend 32 minutes a day exercising, then you will get about a 79 on the test. Okay, so here is the part of this section that's different, because what we just did, that wasn't really different than the last section. What we're focusing on in this section, or in this video, is that reasonable and is it reliable? And so the way we can tell, first of all, is it reasonable? You just look at this problem and you say, the first two would be about here, in between 30 and 35. And then 79.28, yeah, that's reasonable. Now, I'm not asking for your personal beliefs. I'm not saying, do you really think that someone who spends 32 minutes exercising can get that score on the test? We just want to know if it makes sense for the data. And it happened to fall between 79 and 80, but even an 81, a 77, any of those would be reasonable because it kind of falls in that general area. Remember, our data is a scatter plot. It is not a straight line. So that the data points just need to be near that line. They don't need to be exactly on it. So yes, it is reasonable. And then, is it reliable? So what we want to know is it within the scope of the data? So again, I go back up here, and 32 minutes is right here in the middle because I go from 25 all the way through 40. 32 is inside that interval of 25 to 40 minutes. So it is reliable because it is within the scope of data. That's the generic way of answering this question. It's reliable because it's within the scope of data. That's the official answer. But what I mean by that is it's between, or let me say what it is. 32 is between, what was it, 25 and 40. Falls right there in that interval of data values we have. We can only use our lines to predict things within our interval. We can't predict things into the future because we don't know what is going to happen to impact that. There's limits to it. For example, I can't, oh, actually this next example will be a good example. Okay, so this next example, 42 minutes. So right away, just going back to that scope of data, 42 minutes is not between 25 and 30. So this is going to not be reliable. Let me just write this down. Reliable? No. And the reason is it is beyond the scope of data. (42) is more than our interval of 25 to 40. So we can't use 42 to predict it. Now we can still calculate it. I can plug it in and I can say y hat equals 0.44 times 42 plus 65.2. And I can say, put that in my calculator and say that equals 83.68 points. But I can't use this chart, I can't use this line of best fit to say, you know what, you should go out and work 42 minutes because work out for 42 minutes because I know that's going to get you a test score around 84 points. It's just outside the scope of data. Because what happens beyond 40 minutes? What happens if at 41 minutes it actually hurts the test score? So what if we have this pattern? What if this happens? What if we have working out, and then the studies show that once you get to 41 minutes, oh, it actually lowers your test score. If you only give me a picture to the left of this line, if you only give me numbers and data that go up, and I don't see what's happening to the right of the line, I can't make predictions to the right of the line because I don't know if it's going to keep going up or if it's going to start going down. I don't know what the scenario is, so we can't guess outside the scope of the data. But anything from 25 to 40, we can make estimates on. So it seems reasonable. The question, is it reasonable and reliable? It seems reasonable. So probably seems reasonable. But it's not reliable because we don't know what happens right after that 40 minutes. Try again. Looking at this table, we have our line of best fit, y hat, right here, and this is explaining the relationship between the temperature and the minutes that you spend watching TV. So according to the line of best fit, what would be the predicted number of minutes spent watching TV for an average daily temperature of 46 minutes? So what I want you to do right now is go ahead and pause the video and work through this last problem, A through D. See how you can do it and come back and check your answers. And we're back. So if I can find my notes, here it is. And so looking at this, we have y hat equals negative 0.66 times 46, because the temperature was our x, plus 88.5. That gives us 58.14 minutes of TV. Is this reasonable and reliable? Reasonable, that makes sense. What if it was 46 degrees outside? I might be watching about an hour of TV. Is it reliable? So let me go back to the temperature. I'm only comparing the x's when I'm asking if it's reliable. And my x's go from 35 to 65. So 46, in this example we're using 46, then yes, it is. So it is reasonable. And then reliable, yes. According to the line of best fit, what would be the predicted number of minutes if it's 10 degrees outside? Well, if it is 10 degrees outside, I will plug in 10. That's going to give me a total of 81.9 minutes. Is that reasonable? Maybe. Probably. Seems like it makes sense. The colder it is, the more TV I'm going to watch. But is it reliable? 10 degrees, and our scope is between 35 and 45. I'm going to say no. It is beyond the scope of data. Maybe this one will be a little easier to understand because it's a lot farther away. But if I think about how much TV is going to, I'll scroll back. If I think about how much TV is going to watch, if it is 35 degrees and you're watching 60 minutes of TV, and the warmer it gets outside, a little bit less. But what happens when it starts snowing? 32. Freezing. Maybe I'm going to be watching 4 hours. Maybe I'm going to be watching 8 hours of TV because it's so cold, I can't possibly want to go outside. So, for the data we're given, we see a linear pattern. But anything outside of that scope of data, I don't know, maybe it goes up really fast with the exponential function. Maybe after 65, maybe it's such a nice day that it just drops off, and goes to 0 after 65. It's such a nice day that I don't want to do that. So we don't know what's happening on days where it is colder than 35 or on days where it's hotter than 65. We don't know what's happening. We only know what's happening right in the middle, so we can only use this picture, and we can only use this line, which describes the picture, for 35 to 65 degrees. So here, is it reasonable? Probably, maybe. Seems like it would be. Is it reliable? No, because I cannot make predictions about numbers outside of my data, beyond the. All right, told you it would be quick. That is all we have for this second video. When we come back, we will a worksheet. I think there's a 12-line worksheet, so we'll do that in the next video. All right, thank you.